Good evening, everyone. I am Mr. Ish. You are joining me for this single question video, rational function. It's going to be a challenging one. I'll show you but a single way of doing it using polynomial long division and a whole lot of algebra, which will come in towards the middle and to the end. We have that rational function there, 5x to the power of 4 minus 2x squared divided by x squared minus 3. It's a rational function with the highest order numerator degree of the exponent polynomial to be 4. In the denominator we have a 2. You see you have 5x to the 4, you have an exponent variable there 4, and in the denominator 2. N is larger than m, so you can ideally use polynomial long division. I refer you to the video I've recently placed on this rational function and polynomial long division, and all of this will be very clear over there. Do your polynomial long division in a way to simplify that expression you have. Remember, this is just a single way of doing it, but it's not a bad way. X squared goes in here 5x squared times, and you got to multiply that back. 5x to the 4 minus 15x squared, you got to minus this cancels out, which is good. You'll have minus 2x squared plus 15x squared, you'll have 13x squared. X squared goes in here plus 13 times. And you can multiply that back, you'll have 13x squared minus 39. Now do your cancellation, here you'll have a 39. Your answer is basically 5x squared plus 13. 5x squared plus 13 plus remainder 39 over x squared minus 3. All of this now represents the decomposed rational fraction using polynomial long division. That 5x squared, that 13 component are easy. Our problem is that 39 divided by x squared minus 3, and that's going to be the aspect which will take a bit of space to handle. What we can do is place some of these components we have here on the top. We have a 5x squared, we have a 13. I've taken that out from this polynomial long division result. We have to basically analyze this now in terms of this derivative, and we have to analyze this in terms of the derivative, but then we'll add that to what we see over there. All of this, remember, these three components, these two and this third component, have come from that. We have to analyze this, and that's going to take a little bit of space. You can push the 39 out, and you're really looking at dx over x squared minus 3. You're looking at something which looks like x squared minus a squared. You're not seeing an arctan come out of here. You're not seeing an arc cotan. You basically have to use trigonometric substitution technique or some other technique, but let's utilize a technique that we're familiar with, trigonometric substitution. Here, a based on the constant here is 3, but since you're going to do square of it, it has to be a root 3. X is going to be what? It's going to be root 3 secant theta. Dx is going to be root 3 secant theta tan theta d theta. All of that has to come right here into this place. 39 dx is root 3 secant theta tan theta d theta, and here you're going to have x squared, which is all of this square, which will be 3 secant squared theta minus 3. And you see everything is taking form. This 39 and that root 3 can come together. 39 root 3. You can isolate the 3 and push it outside. You'll have over 3. And then you'll have a secant theta tan theta d theta. And here you'll have a secant squared theta minus 1. Remember, tan squared theta plus 1 equals secant squared theta. And then secant squared theta minus 1 equals tan squared theta. So in this place right here, you can put a tan squared theta. We're not doing anything over here which is wrong. We're doing everything here which is right. You have a secant theta tan theta divided by tan squared theta. You can cancel out this one tan theta and you can get rid of the square. And let's make it clean. We're looking at a secant theta divided by tan theta. But if you're doing that, you might as well do 1 over cosine theta divided by sine theta over cosine theta, which is this broken down. These will cancel out. You'll have 1 over sine theta, which is cosecant theta. All of this will simplify into cosecant theta d theta, and there's an integral cosecant theta which we learned in trigonometric integrals, and it has a good antiderivative. The only problem, that good antiderivative is a bit complicated. Well, I guess technically it's not that good then. Anyhow, when you simplify this, you have a 39 root 3 divided by 3. It becomes a 13 root 3, because 39 divided by 3 is a 13. You have a 13 root 3 over here. And remember, I'm doing all of the simplification because I have space and time consuming procedures coming up. I have 13 root 3 minus, the antiderivative of this is a minus natural log cosecant theta plus cotan theta. It's just that I've pushed that minus right here with that. Now we have to evaluate everything here with regards to this theta and what we see over here. Let's come over here. Theta over here is equal to arc secant x over root 3, which from when you develop this triangle, x over root 3 helps you develop this x squared minus 3, and you're looking at that. Now you have to plug these in based on what you see. And let's come over here. We have minus 13 root 3 natural log. Cosecant of this angle is hypotenuse over opposite, x divided by root x squared minus 3, plus cotan of this angle is root 3 over square root of x squared minus 3. Now the algebra part begins. The algebra part is everything which relates to this natural log, and then of course we have to add everything here to the end. We'll keep that because that's what has led to this entire procedure. Let's look at everything within this absolute value. We have this, we'll come over here, we have this minus 13 root 3, and now here let's look at everything here in the absolute value. We have an x plus root 3. Forget everything else, we're doing the algebra part for this absolute value parentheses portion. We have this right here in the bottom, x squared minus 3. This part can be looked at using a different way. We're looking at x minus root 3, and then we're looking at x plus root 3. If you were to multiply this, you'll get that, and you know you will. It's just properties of radicals. Look at this in a better way, and let's do that. We are looking at x minus root 3 to the power of 1 over 2, and then we're looking at x plus root 3 to the power of 1 over 2. I'm just making things clarifying or clear, because when you're looking at radicals, it becomes confusing. All of this has converted to all of that, and let's bring that into the picture. We're looking at this, x minus root 3 to the power of 1 over 2, and we're looking at x plus root 3 to the power of 1 over 2. Remember, this is everything right here within the absolute value, or out of which is this natural log and all of that. Now, when you're looking at this, you have this to the power of 1. This and this can cancel out. This cancels out such that it makes this to the power of 1 over 2. You see that? We have x plus root 3 divided by x minus root 3. Each is under a radical, but you might use properties of radicals and bring them all under a single unifying radical. And you might use properties of radicals once more and bring everything under parentheses, but in this way right over here. All of this has given you that, and I want to bring that into picture right over here. And remember, you can always rewind and look at all of this again. We're looking at minus 13 root 3 natural log. Maybe I don't need this part over here. If you take this 1 or 2 using the properties of logarithms, you can bring it out as a coefficient and you'll divide. You'll have a minus 13 root 3 over 2. Remember, exponent and coefficients can switch back and forth. Natural log x plus root 3 over x minus root 3. You could even technically open this up, and technically you'd have everything here under absolute value, which I'll bring at the end. So this is what I've gotten from all of this right here. It's not 100% simplified, but it's simplified enough for now. Let's come back, erase all of this, and bring everything into the picture right over here. We have all of this adding right here, but this right here is the antiderivative. Here we still have to determine the antiderivative, and it's not hard. This plus becomes a minus by means of that. Minus 13 root 3 over 2 natural log absolute value x plus root 3 divided by x minus root 3. We still have to do something here, and we will. I guarantee you that we will. Now we have come to this. The antiderivative of 5x squared is a 5x cubed over 3. For that is a plus 13x. Now I want to use the properties of natural logs again. Root 3 over 2. I'm looking at here a quotient of logs, which is the same thing as a difference of logs under their individual logs. Natural log x plus root 3. Let's bring a parentheses right over here, because now this quotient becomes a minus, and then we have 13 root 3 over 2, because this 13 root 3 over 2 coefficient affects both of these logs, which I'm bringing out from right here. I want to erase this part right over here because it's in the way, and I have coming from here natural log absolute value x minus root 3, and then we close this big parentheses right here. It can be a little confusing, but if you follow it through, it works. Let's write everything here again. 5x cubed over 3 plus 13x, open up the parentheses, minus 13 root 3 over 2. natural log x plus root 3. This minus and this minus will become a plus. 13 root 3 over 2 natural log absolute value x minus root 3, close the absolute value, bring a plus c, and that looks right there to be a good final answer. As a final step, if we want, we can do a common denominator over here and bring this under a common denominator, which I will. 5x cubed plus 39x, right? 39x over 3. We'll keep this under its separate denominators. 13 root 3 over 2 natural log absolute value x plus root 3, close that, and then we have a plus 13 root 3 over 2 natural log. We'll create a new absolute value x minus root 3, close that, and plus c, and that right there is the final answer of this rational function. You can see it was a rather elaborate and lengthy process. That entire trigonometric substitution procedure is what complicated this entire rational function integration, but it has been completed. And with that, I thank you for watching this video. Stay tuned. Have a nice day.